It's Paul again with a script designed to show you how to deal with a situation where you have two random variables and a generalization of the normal distribution called the bivariate normal distribution. I had to do a little bit of digging to get this to work in R, but finally I discovered that if I install a package capital MASS, I'm sure that's an acronym for something, but I don't know what, then I have access to something that generates multivariate random normals. As usual, you run install packages once and only once. I've commented it out, but remove the comment marker the first time you run this script, and then the library will give you the function that you want. Here's how this function works if we want just independent standard normal variables. The second parameter is a vector of means, and since we want standard normal, the means are both going to be 0. The third parameter is a so-called covariance matrix. We want two independent random variables, each with a variance of 1. So the matrix that I want to supply, sigma, is just the identity matrix. Now I call MVR norm. The first argument is the number of samples I want. Second, the means. The third, the covariance matrix. And we're spewing out a bunch of numbers. Can't tell much, but in fact, each of them is drawn from a normal distribution. Let's generate 10,000 samples and get a closer look. If you look at these, you'll see that sometimes one is positive and the other is negative. Sometimes both have the same sign. And sometimes they're bigger than one, sometimes they're smaller than one. Let's do a bit of statistical analysis. For the first column, the mean is very close to 1, and the estimate of the population variance is, the mean is close to 0. The estimate of the population variance is close to 1. Same thing is true for the second column, and the effect of using that diagonal matrix as sigma is that the columns are uncorrelated. That is, if I take the product of the two entries, on the average, I get 0. If I call the R function VAR on this matrix with a pair of columns in it, it obligingly gives me the variances on the diagonal and the covariances off the diagonal. And you see we put in the matrix 1, 1, 0, 0, and from our 10,000 samples we got fairly close to that. How are we going to look at this stuff? Well, it's two-dimensional, so we can do a scatter plot. All I do is say plot first column, second column, using a period as the character and setting ASP. That's not a venomous snake, it's the aspect ratio. It says in the plot use the same units for X and Y. And we get lots of little dots, more of them toward the center, fewer off on the edges, and because I use this period, they're fairly separate. If you use the default character here, you get a bunch of little circles that overflow on one another and don't look very good. Now let's introduce some correlation. Correlation is generally symbolized by the Greek letter rho, so I'll set rho equal to 0.6 and put rho in the off-diagonal entries for my covariance matrix and generate a lot of samples. Look at the first column. Got a sample mean of 0, a sample variance of 1. Second column, mean of 0, sample variance of 1. But now, when I take the product of the two entries and average it over my 10,000 samples, I get a number that's very close to 0.6. I now have a correlation of 0.6 between these random variables, and in the lecture I've described how to deal with that in terms of integration and change of variables. The function VAR gives me back the covariance matrix for my samples very close to what I put in. Of course, the more samples I choose, the closer this will be to my input. And now when I do a scatter plot, the correlation becomes very obvious. When X is positive, Y is likely to be positive also. That's the effect of this correlation. If you used a negative value for rho, you would discover that the scatter plot ran down the other diagonal. I can go a little bit further. I can change the variances too. So I will introduce two names for the new entries, sigma.x and sigma.y. These, by the way, are variances, not standard deviations, and it's a little bit unconventional to be using sigma for a variance. Usually it's called sigma squared, but since the author of this package likes to call the covariance matrix sigma, I've stuck with that convention for its entries. Okay, so now we've got a covariance matrix with only diagonal entries, but now a 4 and a 2. Generate a lot of samples and see what we've got. The first column has a mean of 0 and a variance that's close to 4. Second one has a mean close to 0, a variance close to 2. Notice, by the way, that even with 10,000 samples, your sample variance doesn't come out always that close to what you put in. You really need a lot of samples to get the variance right. There's the entire covariance matrix, very nearly diagonal, very nearly 4 and 2 down the diagonal. And if I look at the scatter plot, I see it's wider in the x direction than in the y direction. And because I set the aspect ratio equal to 1, that's a valid conclusion. 1 unit on the x-axis is the same as 1 unit on the y-axis. Now we can go whole hog and reintroduce some correlation. To get the off-diagonal entries now, I have to take the correlation coefficient rho and multiply it by the product of the two standard deviations. That is, multiply by the square root of the product of the variances. So here is now my sigma. It is no longer a diagonal matrix. And when I generate lots of samples, well, I can't draw much of a conclusion by just looking at a few of them, but with all 10,000, I see first column has mean 0, variance 4. Second column has mean 0, variance 2. But when I take the mean of the product of the entries in the two columns, I get a number that's different from 0. In fact, it's very close to that off-diagonal entry in my covariance matrix. And if I ask R to calculate the correlation, it gives me back a number that's remarkably close to 0.6. There's my covariance matrix, and this is the general case for bivariate normal random variables. They can have different variances, and they can be correlated. And if you look at the scatter plot, you can see, well, it's sort of stretched out along x, less stretched out along y, and the fact that it tends to concentrate along the main diagonal means the two variables have a positive correlation. You'll have a chance to try this out on a data set that I've put together where I've got a collection of math and verbal SAT scores in the two columns. They are correlated, and you can try modeling this with a bivariate normal distribution. Now let's go to another topic where we will need the multivariable calculus we're developing. We're thinking about the sum of normally distributed random variables, and I just want to convince you by example that in this case the sum is also normal. This is proved in the lecture notes. So we'll take 10,000 samples from a standard normal distribution, but these will be samples of size 2, and I will take the sum of the two samples and store it in a vector called mySums that will hold 10,000 of these. Plot a histogram of the result. Well, that looks mighty normal, doesn't it? But it's not a standard normal distribution. It's a normal distribution where the mean is still 0, but the variance, you could have guessed this, is the sum of the two variances. So this is a normal distribution with variance 2. You already knew that for independent variables, the variances as well as the means add up. What this is showing you is the additional fact that if you're adding together normal random variables, the sum is also normal, and the mean and variance tell you everything. If I look at the sample variances, they're not precisely right, but they're close. I can even sum samples from different normal distributions. So what I'm going to do now is take a sample drawn from a normal distribution with a mean of 4 and a standard deviation of 3, that is a variance of 9. Add on to that a single sample from a distribution where the mean is 6, the standard deviation is 4, and the variance is 16. I plot a histogram. Big surprise, it's normal, and I know what normal distribution will match. I add the means to get 10. I add the variances, 9 and 16, to get 25, but curve for dnorm wants me to give the standard deviation, the square root of the variance, so I feed it 5 as a parameter. Bingo! It matches the histogram almost perfectly. Now let's try the same thing with random variables that have an exponential distribution. I'll play exactly the same game. I will generate 2 samples from an exponential distribution with parameter 1. And in this case, the sum does not satisfy an exponential distribution. That property, that the distribution for the sum is the same as the distribution for the things you added together, is unique to the normal distribution. In this case, however, we do get a vaguely familiar distribution. This sum is a gamma distribution, and the shape parameter for the gamma distribution is 1 plus 1, because the exponential distribution is a gamma distribution with shape parameter 1. So if I fit d gamma with shape parameter 2, rate parameter 1, it matches the histogram almost perfectly. And you can even add several exponential random variables together. This is going to be important for data analysis because frequently what you're doing in data analysis is looking at sums of samples. And it's nice to know theoretically what happens when you add together samples from various distributions. So I'll do the same thing, one small change. In this case, I will generate 5 samples from an exponential distribution and take the sum. And there's the histogram. Well, it goes up, swings down, has a long tail. That looks vaguely gamma-ish, and in fact, it's precisely a gamma distribution, but now the shape parameter is 5, and you can now see we've got a couple of interesting things to try to prove. That when you add normal distributions, the result is normally distributed. When you add exponential distributions, the result is something that has a gamma distribution. And in fact, if you add 2 random variables from gamma distributions, you again get back a gamma distribution, but with a larger value for the shape parameter.